Today we're going to talk about polyatomic ions, and we're going to first off take a look at how compounds with polyatomic ions can be named and formed. The rules are basically the same. We know that polyatomic ion compounds have an overall neutral charge, just like regular monatomic ion ones do. And we also can find the formula by swapping charges, just like we normally would. Here's an example. Say we wanted to make a formula for a compound that occurs when potassium ion, K+, remember because it's column 1, bonds to a polyatomic ion called nitrate, which is NO3 2-. I put the K down here, write cation first, nitrate, NO3 1-, and here I have equal and opposite charges, so I won't have any subscripts. This formula just ends up being KNO3. Now it does have a subscript, that 3, but that was there as part of the polyatomic ion, so that won't change. Here's another example. Sodium ion, again another group 1, bonding with sulfate, which is SO4 2-. Cation first, Na+, and then the anion, SO4 2-. Now I'm going to charge swap. This 2 is going to go after the sodium, and then this 1, well, it's not written because 1s are just implied. So Na2SO4 is my formula. Still a subscript here, but it's not anything new that wasn't there before. Here's another example. Calcium is column 2, so it's 2+, and here's a polyatomic ion phosphate, PO4 3-. Cation first, 2+. Anion next, 3-. Charge swap is indicating that 3 is going to go there, and this 2 is going to go there. So I could write Ca3 PO4 2. Now, there's a little bit of confusion here because this looks like 3 calciums, 1 phosphorus, and 42 oxygens. That's really not what I have here. I have 2 PO4s and 3 calciums. So a set of parentheses eliminates the confusion. Anytime you put a subscript on a polyatomic ion, just put parentheses around the ion first, and then people know exactly what you're talking about. Here's another example. Ammonium is a polyatomic cation, NH4 1+, bonding with sulfate that we've already seen before, SO4 2-. So I write cation first, anion second, and then I charge swap. 2 goes after ammonium, so I'd write NH4, but I'd put it in parentheses because it's polyatomic. Before I put the subscript 2. And then SO4 really doesn't have a subscript because ammonium's charge was 1. One more. Here's barium ion. Barium's 2+ because it's column 2. And then here's a sort of a long, complicated looking polyatomic ion, C2H3O2. It carries a 1- charge. When I charge swap, barium gets a 1, and acetate, C2H3O2, gets a 2. So I have to enclose it in parentheses before I write that subscript 2. Try this one. Write a formula for a compound that forms when potassium ion bonds with sulfite, SO3 2-. Here's your answer. Potassium's 1+, SO3 is 2-. When I charge swap, K gets the 2, SO3 gets nothing. Try this one. Write the formula for a compound that forms when aluminum, which is 3+, bonds with nitrite, NO2 1-. Here's your answer. Aluminum is a cation, 3+, nitrite, NO2 1- is the anion. After charge swapping, we see aluminum has no subscript, the implied 1, and nitrite, NO2, is going to have a subscript 3. So I enclose it in parentheses, then I put the 3. Try lithium with phosphite, PO3 3-. Here's your answer. Lithium has a 1+ charge. Phosphite, PO3, has a 3- charge. When I charge swap, lithium's going to get the 3. Phosphite is going to have no subscript except the 3 that was already there. Well, it would be important to know some of these polyatomic ions so that you can recognize them when you see them in a formula, or when you see their name in a name for an ionic compound. So we're going to take a look at a list of polyatomic ions that you should know. This is your first introduction to them. You'll get another list that you can carry around permanently, and you should begin memorizing these. It's going to be important for you to know these. We have one polyatomic ion on our list that has a 1+ charge. This is our only polyatomic cation, and it's called ammonium. Ammonium is NH4, carries a 1+ charge. We have a bunch of 1- ions, just kind of miscellaneous 1- ions. Acetate we've seen before, C2H3O2, 1- charge. Or sometimes it's written, especially by organic chemists, as CH3COO with a 1 minus charge. Another one is cyanide. Cyanide is a carbon and a nitrogen, CN, with a 1 minus charge. Hydroxide is a really important one. There's a whole class of very important compounds called bases that all have hydroxide in them. So OH minus is hydroxide. Nitrate is NO3 1 minus. Nitrite is NO2 1 minus. With nitrate and nitrite, we see a trend that's going to show in all names of polyatomic ions. Just to review here, what we just had on the screen, nitrate was NO3 1 minus. The difference between the 8 and the ite is how many O's are there. Ite means fewer O's, here we have 2, and 8 means 1 more O, there we have 3. Here's another ion, permanganate. This actually has a metal in it, manganese. It's MnO4 1 minus. This shows up a lot in a kind of chemistry they would call redox chemistry. This is a strong oxidizer. And then we have 20 ions that are based on the halogens, and we have a little trick to remember what they are, but they follow a definite pattern. Where X is any halogen, like here are the halogens, for example, fluorine, chlorine, bromine, and iodine. There's also astatine, but we're not going to see that. So substitute for X any one of these, and you have this pattern. X minus is that halogen ending in ide. Well, this is just a monatomic ion. So for example, if I was doing chlorine, Cl1 minus, that's chloride. F1 minus would be fluoride. So you just substitute for X the word part that begins the halogen. If you have XO with a 1 minus charge, well, this is a polyatomic ion involving that halogen. It's hypo, and then the word part for the element, and then ite. So ClO 1 minus I would call hypochlorite. Start with hypo, end with ite, chlor in the middle. Hypo is a word part that means under or less than. So if I take the hypo away, I have more O's. So you see I go from XO in hypoite to XO2 in ite. So for example, ClO2, 1 minus charge, they're all 1 minus charge, all these ions, is going to be just chlorite. 8 is always 1 more O than ite, so X8 would be an example like this, ClO3 instead of ClO2 with a 1 minus charge. And I would name this chlorate. 1 more O than chlorite. And then there's another word part that means a relative quantity, and that's per. Per means more or beyond. So per X8 means more O's than 8 even had. So 8s were XO3s, per 8s are XO4s. So for example, ClO4 1 minus would be per chlorate. There's a goofy little phrase that has no meaning except for to remember these ions. It's called I'd hit it at perats. And these words, I'd hit it at perats, are really indicators of the prefixes and suffixes that are going to show up in these polyatomic ions that have halogens in them. Ide stands for, of course, ide. And that means 0 O's. 1 O is hit. Hit is actually hypo for the H, that's the prefix, and ite for the suffix. So that's what hit stands for. It is ite, and that's 2 O's, 3 O's, at, which is 8, and perats is per 8, and that's 4 O's. So we have this sequence of 0 O's, 1, 2, 3, and 4 O's. That this phrase helps us remember what the word parts are. So perats is per, and then suffix 8. So example, let's use fluorine. F minus, FO minus, FO2 minus, FO3 minus, FO4 minus is ide, it, at perats. So ide would be fluoride, and then hypo fluorite, and then fluorite, and then fluorate, and then perfluorate. We have a bunch of 2- ions that we need to have in our memory bank too. One of them is carbonate. This is fairly common. Carbonate is CO3 with a 2- charge. We also see chromate. This is another one like permanganate that has a metal in it. CrO4, 2- charge. Oxalate is C2O4, 2-. Peroxide is O2, 2-. This confuses a lot of people when they start writing formulas because we're used to oxygen being O2- as a monatomic. This is actually a 2-atom diion, polyatomic peroxide. Both atoms happen to be oxygen, but it's still polyatomic. Sulfate is fairly common, SO4, 2-. Sulfite, notice this 8-ite suffix change. That means ite means 1 less O, so SO3, 2- is compared with SO4, 2- for sulfate. This one not as common, S2O3, 2-, thiosulfate. Then we got a couple of 3- ions that are going to show up fairly commonly. Phosphate is one, PO4 with a 3- charge. And the second one, phosphite. And of course, ite means 1 less O, so this is PO3, 3-, as compared to phosphate's PO4, 3-. This is by no means all the ions that exist. There are tens of thousands of them, but these are the important ones, the ones that are going to show up the most often and the ones that you should have at the tip of your memory. There are also some acidic anions. If you take any of the anions practically from the lists above and do a little modification, you can create some more acids that are also on your list. So you start with any anion from the lists that you had up above, and then add an H to the front of the formula. What that does is it changes the charge. It makes it one step more positive than it was before. And what it does to the name is it adds the word part bi or hydrogen, your choice, either one, to the name. So let's do an example, starting with the carbonate ion. This is just as a base, carbonate. If I add one H to it, it becomes HCO3 and carries a 1- charge. Notice my charge changed from 2- to 1-. I call this bicarbonate. Or as an alternative, I could call it hydrogen carbonate. If I added another H to it, my charge would be up to neutral. 1- would change to neutral. And when we've done that, we come up to an acid. This acid is called carbonic acid. Any acid whose root ion starts with 8 is going to end in ic, carbonate, carbonic acid. You can remember that by thinking if I ate something that doesn't taste good, I might say ick. It's one way to keep it straight. There are other memory tools as well. Another example, sulfate, SO4, 2-. If I add an H to it, I have HSO4, 1-, and this is called bisulfate, or some people call it hydrogen sulfate. If I add two H's, H2SO4, now I have sulfuric acid. Because I started with 8, my anion, the acid name, is going to end in ic. This is 1 less O, so this is sulfite. If I add an H, I have HSO3, 1-. That's hydrogen sulfite, or bisulfite, some people might say. I add two H's, and I have sulfurous acid. So if the ion ends in ite, the acid will end in us. Here's a memory tool one of my students developed a few years ago. Mouse bite, ice skate. 8, ick, ite, us. Maybe that'll help you. Here's phosphate. Add an H. I have HPO4, 2-. Name hydrogen phosphate. Add another H. H2PO4, 1-. This would be called dihydrogen phosphate. Add a third H, and now I have H3PO4, and this is the acid. And because this started with 8, this is going to be called phosphoric acid. This is phosphite. Give it a try. If I add an H, got HPO3, 2 minus, hydrogen, phosphite. Add 2 H's, H2PO3, 1 minus, dihydrogen. Phosphite. Add 3 H's, and I have the acid. Because this started with ite, this is going to be phosphorus acid. Ends in ite, acid ends in us.